Welcome to the Building Ethernet LANs module. Now that we have learned about network models, layers, and addressing, let's move on to the next topic, Ethernet LANs. In this section, we will delve into basic Ethernet operations as well as cover repeater, hub and bridge operation, and Ethernet switch operation. Today's complex networks are built using many different network devices. The names of these devices might be familiar to you and include routers, switches, and more. But to understand what these devices do and how they work, we first need to take a look back in time. Networks have grown at a pace not anticipated even a few years ago. Worldwide, more than 1.6 billion PCs were in use by the end of 2011. New network devices have been developed along the way to address specific problems resulting from this growth. To understand the different network devices used in today's networks, it's helpful to understand the predecessors to those devices. To gain that understanding, we are going to take a look at the history of a fictional company called Acme Company, from its roots in someone's garage to that of a multinational company. When Acme Company was established in the mid-1980s, the company had only a few PCs. Their networking needs were pretty simple. They needed to share documents and spreadsheets as well as a single printer. In networking terms, PCs and printers are known as end-user devices, hosts, or just devices. As we mentioned in Section 1, a geographically limited network is called a local area network, or LAN. To create a LAN, end-user devices must be connected either physically with cables or wirelessly. A LAN also requires a set of rules controlling communication on that connection, and the most common set of rules is called Ethernet, a LAN network technology developed in the 1970s. Ethernet is a set of standards that define rules such as frame format, as well as how computers communicate with each other over a single wire shared by all devices on the network. These rules give any new device attached to the wire the ability to communicate with any other attached device. Although Ethernet technology has evolved considerably since it was first implemented, the fundamental operations remain the same. Ethernet standards include a number of components. First, there are the physical layer characteristics. In other words, what does the physical layer, or layer 1, consist of? Next, there is the protocol that controls access to the network, and finally, there is the frame format. We will cover all of these components. Ethernet was originally deployed with multiple computers connected to the same physical wire or cable. This physical network topology or layout is called a shared bus, meaning that when one computer transmits data, all other devices on the shared bus or network segment receive it. If there is a break in the cable, devices can no longer communicate. By the way, the term network segment means different things to different people. In this course, the term network segment, or simply segment, refers to the group of network devices that compete with each other for access to the wire. To refer to the actual cable or wire used to connect network devices together, we'll use the term physical cable segment. Let's look at the functionality of network segments in more detail. How do end-user devices connect to the network segment? And because multiple end-user devices can't connect to the same network segment, how do devices know when it is their turn to send data? Finally, because all devices receive the data, how does a device know that the data is intended for that device? We'll answer all three of these questions in this section. To connect to the network segment, a device uses a Network Interface Controller, or NIC, and Ethernet cabling, or a wireless NIC. Ethernet operates at layers 1 and 2, which you might remember are the physical layer and the data link layer. Both of these layers are implemented on the NIC. The Ethernet physical layer defines such things as the connection speed and the type of cabling. Both have evolved over time and are discussed later in this section. Click the Additional Information button to learn more about NICs. A Network Interface Controller, or card, is a computer hardware component installed on a computer or printer so that it can be connected to a network. The terms NIC, network adapter, network card, and LAN adapter are used interchangeably. In the 1980s, a NIC was an expansion card that plugged into a computer bus. Today, most computers have a NIC built into the motherboard, and a separate card is not required unless you need connections to multiple networks. NICs on personal computers today commonly use either Ethernet cabling or a wireless connection. A wireless NIC with a USB interface can easily be added to almost any computer. The second component we mentioned previously was the protocol controlling access to the network or wire. That is, how do devices know when it is their turn to send data? Access to the physical wire or segment is controlled by a Media Access Control or MAC protocol. Ethernet in particular uses carrier sense multiple access with collision detection or CSMA-CD as its MAC protocol. Other MAC protocol exists for other technologies. To understand CSMA-CD operation, think of a group of people having a conversation. As we discussed in Section 1 on protocols, in general, human conversations work only when one person talks at a time. That way, everyone in the group can hear and understand what is being said. The same is true of computer networks, and in the case of Ethernet LANs, the CSMA-CD protocol regulates the conversation. If a device has data to transmit, it listens on the wire to see if any other device is transmitting. If the wire is idle, the device sends the data. All other devices on the segment receive the transmission. Now, what's important to remember about the CSMA-CD protocol is that it allows a network device to either transmit data or receive data, but not to do both simultaneously. This type of system is known as half-duplex communication. A half-duplex system provides for communication in both directions, but only one direction at a time. Half-duplex data transmission is similar to using a walkie-talkie. If you want to talk, you need to press the talk or transmit button. While you are talking, the other person cannot transmit to you. Full duplex communication, on the other hand, sends and receives data at the same time. We discuss full duplex communication in more detail later in this section. On a network using half-duplex communication, when one device on a network segment is transmitting data, other devices cannot transmit data. Any device that needs to send data must wait until the line is clear. Well, all computers listen to the wire first to make sure the wire is idle before they send data. Sometimes data collisions do occur. Let's return to our conversation analogy to see how this problem can happen. If there is a lot of conversation and two people try to say something at the same time, others in the group might not understand what either person is saying. At this point, one person stops for a moment and allows the other person to resume speaking. The same thing could happen if two devices listen to the wire, believe it is idle, and try to transmit data at the same time. This condition is known as a collision, and this is where collision detection, the CD part of the CSMA-CD, comes into play. When a collision occurs, both transmitting devices stop transmitting, wait a random amount of time, and attempt to transmit again when the wire is idle. Click the Additional Information button to learn more about how collision detection works. In half-duplex Ethernet networks, after a device transmits data, it listens to the network and expects to hear the same data in the exact same pattern. If the device hears a different pattern, it assumes a collision has taken place. When a collision occurs, both transmitting devices send a jam signal. This jam signal indicates to all other devices on the segment that there has been a collision and they should discard the partial frame they have received. The jam signal also causes all transmitters to set a random retransmission timer, reducing the probability of a collision when the first retry is attempted. When each device's timer expires, they begin the transmission process again, hopefully at different times. If another collision occurs, the timers are set to randomly longer periods of time until the frame is successfully transmitted. A network segment is also known as a collision domain with CSMA-CD. As more devices are added to the network segment or collision domain, more collisions occur, degrading the overall network performance. The increasing frequency of collisions was a major obstacle in the development of networks. We'll see shortly how network designers overcame this obstacle. Now let's move on to the third question posed earlier. How do devices know which data is intended for them? Let's begin by looking at how data is encapsulated. When a device needs to send data, the NIC encapsulates it into an Ethernet frame. The NIC professes each frame with a preamble and start delimiter. This specific 8-byte sequence shown on screen allows receiving devices to recognize the start of a new frame. The preamble and start delimiter are not considered part of the Ethernet frame itself. Ethernet standards define the Layer 2 frame format, which has evolved over time. You might hear people use the terms Ethernet and 802.3 together or separately. Click the Additional Information button to learn more about Ethernet evolution and the term 802.3. Ethernet is the most popular and most widely deployed network technology in the world. You might have also heard the term 802.3 used in reference to Ethernet. The origin of that term actually goes back many years and warrants an explanation. Historically, the term Ethernet actually referred to a family of technologies that included LANs and Metropolitan Access Networks, or MANs. Recently, Ethernet has been implemented as a wide area network, or WAN technology as well. Ethernet was originally developed by Xerox and then standardized by DEC Intel and Xerox. This standardization version is referred to as Ethernet version 2. Soon after, the Institute of Electrical and Electronics Engineers, or IEEE, created a committee to standardize network technologies. Since then, different subcommittees have worked on different aspects of networking. Each subcommittee is assigned a unique number that is appended to the working group number. For example, the 802.3 group standardized the operation of CSMA-CD. The 802 committee was also interested in standardizing different networking technologies, such as Token Ring, which is 802.5, as well as a method of supporting alternative Layer 3 protocols, which is 802.2. Many people are familiar with the term 802.11, which defines wireless standards, because the IEEE standard differed slightly from the DEC Intel Xerox standard. The frame formats also differ slightly as shown on screen. The 802.3 frame format includes a logical link control, or LLC portion, which allows Layer 3 protocols other than IP access to the wire. Examples of other non-IP protocols include Apple Computer's AppleTalk and Novell Networks IPX, the discussions of which are outside the scope of this course. Well, Ethernet and 802.3 differs slightly in their terminology and their frame format. Their media access control, or MAC protocols, are virtually identical. Today, the term Ethernet refers generically to both sets of Ethernet standards. The Ethernet frame includes the destination Layer 2 address of the device receiving the data, as well as a source Layer 2 address of the device sending the data. Each NIC has a unique Layer 2 address that is assigned by its manufacturer. The manufacturer burns this address into a programmable read-only memory, or PROM chip, on the NIC. The NIC uses this address as the source address in a frame. For the destination address, it uses the address that is burned into the NIC on the receiving device. A Layer 2 address is also known as a hardware address, a physical address, or a MAC address. In this course, we will use the term MAC address for a Layer 2 address. Click each field to learn more about the Ethernet frames. The destination address is the Layer 2 or MAC address of the device that will receive the frame. The source address is the Layer 2 or MAC address of the device that is sending the frame. The type field identifies which Layer 3 protocol is being transported in the Ethernet frame. Protocol types include IP, AppleTalk, IPX, or something else entirely. This field is the only one that differs between the Ethernet 2 and 802.3 frame formats. In an 802.3 frame, this field indicates the length of the frame. The data field contains the original data created by an application, as well as the headers that have been added by each layer during the encapsulation process. Note that at layer 2, we do not deal with any of the information added by the other layers, but treat it all as one piece of data. The checksum field includes a cyclic redundancy check, or CRC, which is a method of checking errors in data that has been transmitted on a communications link. Let's take a closer look at MAC addresses and how they are used by a device. A MAC address is a 48-bit or 6-byte address that uniquely identifies a device's NIC. We will cover bits and bytes in detail in Section 4. But for now, understand that a byte is comprised of 8 bits of data, so 6 bytes is the same as 48 bits. Take a look at the MAC address on screen. MAC addresses are typically expressed in hexadecimal format, a numbering system that uses 0 through 9, but that also represents numbers greater than 9 using the letters A through F. We will discuss this and other numbering systems in Section 4. Each digit represents 4 bits, so 1 byte, which is 8 bits, is represented by 2 digits. For example, in this MAC address, 00 is the first byte, 90 is the second byte, and 69 is the third byte. The bytes in MAC addresses are displayed using dashes, colons, or dotted decimal format as shown on screen. Breaking down MAC addresses further, each is broken down into 2 components. The first 3 bytes of the MAC address comprise the Organizationally Unique Identifier, or OUI, that every Ethernet equipment manufacturer is assigned by the Institute of Electrical and Electronics Engineers, or IEEE. In our example, we have used 00, 90, 69, which is the Juniper Network's OUI. The manufacturer then uses the remaining 3 bytes to assign a unique number to the NIC. When the NIC is ready to send data, it adds the destination and source MAC addresses into the frame and transmits it on the segment. To keep our animation simple right now, we will just show the destination address on the frame designated with the letters DA, because Ethernet is a shared medium. Every device on the segment receives every frame and compares the frame's destination MAC address with its own MAC address. If the destination MAC address does not match, the NIC discards the frame. If the destination MAC address matches, the NIC processes the frame. First, the NIC compares the cyclic redundancy check, or CRC checksum, on the frame received with the CRC that was generated by the sending computer. Next, if the frame length is the same and the CRCs match, the NIC examines the frame type to determine the upper layer protocol. Then it strips of the Ethernet frame and forwards the data to the appropriate upper layer protocol. Before we close out the subject of MAC addresses, there is one more detail we need to cover. So far, we have been talking about MAC addresses that are unique to both the sending and destination devices. That is when one device sends data to another device. The destination MAC address is a unique MAC address, which is also known as an individual or unicast address. But what if one device is sending data to multiple devices? This scenario requires a MAC address as well, but of a different type. If a device needs to send the same data to every device on the network, it uses a broadcast destination MAC address. This special address used for broadcasting is shown on screen. If a device needs to send the same data to a group of devices on the same network, it must use a group address or multicast MAC address. Multicast addresses always have the first bit of the first byte set to 1. Unicast, broadcast, and multicast addresses are all hexadecimal addresses. Let's return to the history of the Acme Company. The company grew at a rapid pace and, needing more space, expanded into nearby buildings. Ethernet has strict rules about the length of a physical cable segment as well as the number of devices on the cable. So, to accommodate this growth and add more computers and printers to the network, Acme Company used a network device called a repeater to extend the length of its Ethernet physical cable segment. A repeater is a physical layer device used to connect 2 or more separate physical cable segments together, making it act like one long cable. A repeater is a simple hardware device that regenerates electrical signals, sending all frames from one physical cable segment to another. Click the Additional Information button to learn more. In a LAN using shared Ethernet access, any data sent over the wire must reach every part of the network or collision domain within a certain amount of time. For this reason, Ethernet physical cable segments, or cable runs, are limited in length and in the number of devices per run, based on the amount of time it takes for a bit of information to go from one end of the wire to the other. Therefore, faster mediums, such as fiber, have longer length restrictions. The table on screen shows the maximum cable length for each type of Ethernet media. In the early 1980s, repeaters were used to extend the reach of Ethernet, as well as to isolate failing cables. However, each repeater that the signal goes through adds a small amount of time to the length of the transmission. To ensure that timing limitations are not violated, the Ethernet standard implements the 543 rule for deploying physical cable segments and repeaters. This rule divides the network into two types of physical cable segments: populated or user cable segments, and unpopulated or link cable segments. Link segments connect repeaters together and cannot contain end-user devices. So the 543 rule means that there can only be a total of 5 cable segments connected through 4 repeaters, and only 3 of the 5 segments can contain end-user devices. The other 2 segments, or link segments, are used to connect the repeaters. Note that the LAN shown on screen is still one collision domain. As we saw earlier, increasing the number of devices increases the number of collisions on the network and decreases the overall network performance. Exceeding the 543 rule would likely result in a network with too many collisions to be functional. Ethernet networks were originally implemented with coaxial cabling. With the introduction of the IEEE 10BASE-T standard in the late 1980s, Ethernet networks started using twisted pair cabling. Click the Additional Information button to learn more about the 10BASE-T standard. 10BASE-T is one of several physical media specified in the IEEE 802.3 standard for Ethernet LANs. The name 10BASE-T comes from several components in the physical layer. The 10 refers to the transmission speed of 10 megabits per second. The base is short for baseband, which means that only Ethernet signaling is carried on the wires. The T refers to twisted pairs of unshielded but insulated wires. The first 10BASE-T networks used voice grade or Category 3 or Cat3 UTP cables. Cat5 and the newer Cat5e data grade cables support higher transmission speeds with lower error rates. Twisted pair cabling consists of twisted pairs of unshielded but insulated wires. It is also known as unshielded twisted pair or UTP cabling. The first 10BASE-T networks used ordinary telephone cabling, which is a type of twisted pair cabling. In this type of cable, there are 4 twisted pairs of wires, 2 for transmitting data and another 2 for receiving data. At this time, a new device called a hub also became available, and Acme replaced their repeaters with hubs. Now, the physical topology or layout of their network changed from a shared bus to a star configuration. In Acme's old shared bus configuration, many devices were daisy-chained together using a single network cable, which meant that if the cable failed or if one device on the cable was causing network trouble, every device on the cable could be impacted. In a star configuration, each device uses its own twisted pair cable to connect to a port on the hub. If a cable fails, it will impact only one device, and if one device is causing trouble on the network, that individual device can easily be unplugged. Like a repeater, a hub simply takes a signal that it receives from one connected device and passes it along or repeats it to all other connected devices. A hub is not an intelligent network device. It does not look at the MAC addresses or data in the Ethernet frame and does not perform any type of filtering or routing of the data. It is simply a junction that joins all the different devices together. Even though each device has its own cable connecting it to the hub, access to the network still operates by CSMA-CD, and collisions can occur on the shared bus inside the hub. Having twisted pair cabling and hubs simplified many networking operations for Acme, but as more time passed and Acme's network continued to grow, network performance still suffered and employees complained. Remember our discussion of the rules governing a group conversation? As more and more people join the group, it becomes more and more difficult to have an uninterrupted conversation or understand what everyone is saying. One way to fix this problem is to break the large group up into several smaller groups, which is how networks handle the same problem. Let's see how Acme divided up their network. The group of Ethernet devices that compete with each other for access, you might remember, is called a collision domain or network segment. A hub operates at layer 1 and makes both sides of the hub act like one very long physical cable, repeating each and every frame. As more and more computers are added to the network, more potential for collisions is created. To break their network up into smaller segments, Acme installed a network device called a bridge. Just like a repeater or a hub, a bridge connects two or more physical cable segments to create one larger network. Unlike a repeater or a hub, though, each side of the bridge becomes a separate collision domain or network segment. So, a bridge can be used to break up a large network into separate collision domains. This process is often referred to as network segmentation. By breaking the large networks into smaller collision domains, the number of devices competing for network access declines, and of course the number of collisions also declines. If a collision does occur, the bridge isolates the collision to a single domain. A bridge operates at layer 2 and helps regulate traffic flow using MAC addresses. Let's see how this process works. On screen is a bridge with 3 ports. Each port is attached to a hub, and each hub is connected to 2 devices. The MAC address of each device is shown next to the device. Ethernet bridges have 3 basic functions: forwarding frames, learning MAC addresses, and controlling traffic. A bridge uses a MAC address table, which is like a database, to help control and limit traffic on a network. Because a bridge is a layer 2 device, it can examine the source MAC address of each received frame. A bridge can then record the source MAC address and the port on which it was received in its MAC address table. Let's see how MAC address tables are built and how they are used to improve overall network performance. When a bridge first powers on, the MAC address table is typically empty. When an end-user device sends out a frame, the bridge receives it and looks at the source MAC address. In the on-screen animation, the source address is now designated on the frame with the letters SA. If this MAC address is not in the MAC address table, the bridge adds it and associates it with the port on which it came in. Next, the bridge examines the destination MAC address. If the destination MAC address is not in its table, the bridge forwards the frame out all of its other ports. This action is also known as flooding. Because the bridge builds a table of addresses when they come in, the bridge eventually learns through which of its ports destination devices are located, so it doesn't have to flood each and every frame out all its ports. When the bridge receives a frame with a destination MAC address in its MAC address table, it can forward or drop it selectively, reducing overall network traffic. If the destination MAC address is in the MAC address table and resides on the same port where the frame arrived, the bridge simply drops the frame, because the end-user device has already received it. It does not forward the frame to the other ports or segments, reducing overall network traffic. If the destination MAC address is in the MAC address table and is located off a different port, the bridge forwards the frame only on that port again, reducing overall network traffic. If the destination MAC address is a broadcast or multicast address, the bridge must always forward it out every other port. Because a bridge is just another device in the collision domain, it follows the same MAC protocol as every other device. It is important to note that bridges never change the destination or source MAC address. They simply look at the destination MAC address to make their decisions.